So, in the last lecture, I introduced you to the notion and mathematics underlying of the quantum Fourier transform. And I hope I successfully conveyed the message that there was really nothing quantum about the mathematics of the QFT. It's just that the assumption is that this calculation will be performed on a physical platform that is a quantum computer, not a classical computer. Okay, so if we did have such a quantum computer, then it turns out, I think this realization is originally due to Peter Shor himself, is that there's one piece of calculation that one can perform very effectively, and that's called the period finding. So today I'm going to give you hopefully a self-contained introduction to what that is and how the quantum computer performing a quantum Fourier transform can efficiently find out about the period of certain function. Okay, so and before I do that, I'm going to introduce a basic setup that will appear over and over again. And the idea is that we have a whole bunch of qubits, n cluster of qubits, a cluster of n qubits, which I describe as the input register. And I think different people use different names, but this is a name I chose to stick with. And then there is another set of quantum qubits, just qubits. It doesn't really matter how many qubits there are. Let's say just there are m qubits that are put together. And they serve as what's called the output register. So a successful quantum computer will consist of product of n qubits system and m qubit system, and each system serve a different purpose, as hopefully be made clear very shortly. So as I said before, these input cluster can realize one of the following state. Input register, not cluster. So the input register state can be simply stated as x, where x is an integer ranging from 0 all the way up to 2 to the n minus 1. And I said I will often use the capital M n to represent this exponentially large dimension of the Hilbert space of the input register. And the overall state is going to be some direct product of the input register state and the output register state. Okay, since I have written 0 for the output register, what it means is that every qubit in the output register is initially set to a 0 state. Remember that since this is a qubit, then each qubit can be either in a 0 state or a 1 state or some superposition thereof. And the assumption is that the initial output state is all set to this simplest possible form, where every qubit is in the state of 0. Okay, and then by some clever manipulation, I will assume that the initial state is a superposition of all the possible states that can be realized by the input register. And we did have seen this sort of superposition with equal amplitude of all the possible states when we talked about the Hadamard gates. So Hadamard gate operation is what makes this sort of state realizable in actual setting. And so by application of the Hadamard gate to each and every one of these input register qubits, we can actually realize such an initial state for the input register side, while keeping the output register side in this simple form. Okay, so there is this tensor product or the direct product symbol that should have been there, but since it's kind of obvious from the context, I will often omit writing this tensor product symbol. Okay, and then I'm going to assume, so this is a part where I am going to be kind of sketchy. I'm just going to pretend that there exists such unitary matrix or unitary operation whose role is to do the following. When this unitary operation acts on such a product state, where the input register is in the state of X, and the output register is in a state of 0, then after applying the this unitary operation UF, the input side of the state remains the same, but the output side is turned into some other state. Okay, so this is some function of x, and the functional value of x can be somewhere between 0 all the way up to 2 to the m minus 1, where m is the number of qubits that form the output cluster. And this m does not necessarily have to equal n, so the size of the input cluster needs not be the same as the size of the output cluster. They can be different depending on the purpose of the calculation that you want to put on a particular quantum computer. But anyway, so I will assume, without much concern for how to actually implement such an operation, that such a unitary operation is indeed possible. Okay, then if I apply such an operation to the initial state that I have just written down, then by the idea of a superposition, I should insert UF here. Then by the idea of a superposition, the outcome will be the superposition of this sort of state, where every x state in the input cluster is accompanied by the f of x state in the output register. And then you sum that over all the possible input configurations with equal amplitude. Okay, so I haven't really specified what f of x is. It can be really any function. It's not important to know exactly what sort of function f should be. But now the key assumption that we're going to make now is that this f is some periodic function. Okay. So to make the situation more concrete, I'm going to assume that the this period f is some factor of the overall n. Remember that n was 2 to the little n number of qubits in the input register. Uh, in a more precise and complete theory, actually, p does not need to be exactly a factor of n, but that tends to make the argument quite a bit more complex. So instead of going into that more general situation, I'm going to specialize myself to this much simpler situation where p is actually one of the factors of the capital N, so that one can write down these n as a product of p and some other integer q. So p does not have to be a prime number because we're not going to be necessarily concerned with the problem of factorization into primes. But p is some integer. And this function that we just introduced happens to have this periodic property that if you change the argument of the function by an amount p, then you get back to the original function. Okay, so to give you more feeling for what's going on, so let me try to plot some pretty arbitrary function, which depending on what x is, may take on pretty complex, really random like situation, such as this one I have just depicted. But suppose that in fact this was not a random function, but in fact this was a periodic function. Okay, so what that means is that after this much period, then copy. Paste. This function actually repeats itself. But just by looking at the graph, it's not obvious that the function repeats itself. And it's going to be even less obvious if the period p happens to be a rather large number, like, who knows, maybe 10 to the 5. It turns out that identifying the period of a function that has such a large periodicity is quite a bit challenging problem for a classical computer. And of course, I won't go into the details of that mathematics, but maybe you can just take it on my word that this is a proven fact in mathematics. Like, the period finding is a difficult mission for a classical computer. But the point is that if we did have a good working quantum computer, then the mission suddenly becomes pretty easy. Okay, so whenever we talk about difficult and easy in computer science, what it really means is that a difficult problem takes an exponentially large time to compute for the answer, and the easy problem requires only a polynomial time to compute the correct answer. That's the criterion, precise criterion. But people often just say that this is a difficult problem and this is an easy problem. But underneath that colloquial statement is this precise mathematical notion of what makes the computation difficult or easy. Okay, so let's say we did start from some initial state, psi I, and we did manage to transform that initial state into this state by the application of this unitary transformation. And now the mission is to identify the actual periodicity of this function through some measurement on this wave function. Okay, so well, it's a pretty confusing notion after all. How do you find the period of a function by making physical measurements on a physical system using electrical signals and oscillators and all sorts of electronics? How do you actually do that? Okay, so here's a quick sketch of how that is supposed to be done. People haven't really done it because they don't have a big enough quantum computer. They have done it for very simple cases where the period p is something like 2, but that's a kind of trivial problem. Even a child can solve that problem without having to buy an expensive quantum computer. Okay, so at the moment, this is a hypothetical issue, a hypothetical task. But nevertheless, let me push on and try to establish a theory for how one might be able to identify the period of a function. So what one has to do now is to perform this quantum Fourier transform on one of these initial input register state. Okay, so what this quantum Fourier transform operation does, of course, this is another sort of unitary operation. Let me remind you once again that everything you do in a quantum computer is one sort of unitary transformation or other. And QFT is just one special kind of unitary transformation. Okay, so the result of performing a quantum Fourier transform on a certain initial state is this one. So it's a superposition, and Y is again one of the input states of the input register. So what QFT does is to make a superposition of all the possible states in the input register with this particular kind of phase vector, which, if I write it out explicitly, is this vector here. Okay. So with this piece of information, let me now turn to our previous function. Our previous function was obtained by performing the UF unitary operation on the initial state. And now I'm going to supplement that UF operation with a second unitary operation that I just called UQFT. So then this is UQFT acting on, let me just copy this expression from the previous slide. Okay. And UQFT, let me remind you, act on the input state it does not act on the output state. Okay, so then the result of doing the quantum Fourier transform on this input-output hybrid state is, let me move to the next line, is UQFT acting on the X multiplied by the output register state. But this is given by that because that's the definition of QFT. So now I'm going to end up with a double sum both over X and Y. And the result is going to be like that. Okay, so now this argument representing the input state and the this argument representing the argument of the function in the output state, they're no longer the same. And we're going to be summing over both of these arguments, X and Y. But it doesn't matter which one of the summations we perform first. Okay, as usual. So we're going to just switch the order of the summation and write down this expression like this. Okay. So this and these are just equivalent expressions, just written out in different manners. And the reason I have written it out in this way is because obviously I want to do this summation first. Okay, so what does this expression look like, or what does this expression mean? So W omega xy acting on this output state. Well, let me restore the more explicit form of these phase factor. But I said that the f is a periodic function. Now, what that means is that f of 0 equals f of p equals f of 2p, etc. And f of 1 equals f of p plus 1 equals f of 2p plus 1, etc., etc. Okay, now what that means is that now this summation can be organized in this fashion. So maybe I should just keep the omega expression. Omega to the 0th power, f of 0, plus omega to the py power, f of p, plus omega to the 2py power, f of 2p, etc., etc. But as I just mentioned, this and this and this, they're all the same states. Okay, so I can then put them into a factorized form, multiplying exactly the same state. Okay, that's cool. And similarly, I can also write omega y f of 1 plus omega, let's see, p plus 1 times y f of p plus 1 plus omega 2p plus 1 times y f of 2p plus 1, etc. But again, these are all exactly the same states. So again, I can put them into a factorized form. All multiplying exactly the same state, f of 1. Okay? And then you have to add an expression like that with an expression like that, etc. Okay, then the end result is again some nice factorized form. Which I'm going to write down explicitly. And it's also in my lecture file, so you can check that as well. Times and the key thing here is that now the argument of this function can go no further than p minus 1, right? Because once the argument exceeds p minus 1, then that function becomes equal to one of the earlier values because of the periodicity. Okay? And now it's time to focus on this prefactor. This prefactor is something quite familiar to us. This is omega 2 times, let me see, what is it? Omega times alpha py, where alpha goes from 0 to q minus 1. But more explicitly, since omega is 2 pi I over n, so I'm going to put everything here. Okay, but remember that n was really p times q, and since we have a p in the denominator and p in the numerator, they fortunately cancel out. So hopefully things will start to look nicer. Times alpha. Okay, and alpha is going from 0 to q minus 1. Okay, so if you're still not following the math, let me try one more repackaging. Like that. So now we can see that this is some geometric series of this phase factor. And now, as is hopefully familiar, this geometric series is 0 unless this factor happens to equal to 1. Then the result of summation will be this number q. Okay, so what this condition implies is that y is a multiple of q. So y can be 0, q, or 2q, and so on. Okay. So now with that revelation, let me get back to this phase factor. And now clearly see that this phase factor, some of these phase factors, is q times some sort of critical delta between y and some multiple of q. And what's the best way of writing that? Let me call this mq. Okay, so and then that should be multiplied by this this f of 0 plus. Okay, so I'm not gonna write that down all over again. Instead, I just use technology. Copy, paste. Good. Okay, so then that's the result of performing a summation in a clever way. Okay, and of course there is okay, so this is it. There's no further summation. Okay, so now we have this result, and now we have to go back to the yeah, so actually we have to go all the way back here. Okay, let's go back. So the result of having performed this two unitary operations in succession, it turns out, is some number q times a summation over y and some nice canonical delta, constraining y to be one of the multiples of q. And then the result is, y multiplying, sorry, I'm going to have to cut and paste this thing again. Copy, paste, like this. Okay, for details, you really have to sit down and sit down hard, and go through all these derivations yourselves. I see no better way of absorbing this this whole thing technically. But anyway, so the point is that after doing this, then this y state, which is a state of the input register, is is not any state, but it has to be a state which is a multiple of Q, etc. Okay, so let me clarify the situation using perhaps an explicit example will help. Let's say n is 15, which obviously factorizes as 3 times 5. So now the point is that after performing these two unitary operations, and let's say my function has a period of 3, which is obviously a very simple case. You can identify the period without relying on any sort of computer, not even a classical computer, but anyway. So the point is that after performing these unitary transformations, the resulting state is some input state 0 multiplied by some, who cares, some sort of output, plus, so now it has to be a multiple of 5. So 5 as the input state multiplied by some other output state, plus 10 as the input state multiplied by some other output state which nobody really cares about. Okay, then the next one will be 15, but 15 is equal to 0, so we don't have to put that in. Okay, so that's the final state that we get. Now we can make a measurement. We can make measurement on this final state and find that when we do measurements on these input state, we will never find any other state in the input sector but these three. Okay, which are all multiples of the integer 5. So from telling the outcome of the measurement, we know that there's this number that stands out, and that number is obviously 5. And 15 divided by 5 is 3. So this is the period. So this is the mafia that has been hiding in the bush. Okay, and we have nailed him. Good. So this is what the period finding is all about. Okay, so actually a more complete argument would have to take into consideration the amount of computational time that's required to finish all of the steps that I have just laid out mathematically. And that's the part that I'm going to skip. That truly belongs to the realm of computer science. And unfortunately, I'm not a very good computer scientist, at least not yet. So if you're interested in that, then you should perhaps refer to more dedicated books on quantum computation. Okay, but other than that, I believe I have conveyed the gist of these period finding algorithm. Okay.